All right. Can you see the screen? Is it visible?
Yes, I can see the screen.
All right. Okay. So last time we were talking about energies, right? Kinetic energy, potential energies, uh, and different various types of energies. Is there any question from anyone regarding any of the concepts that we have discussed so far?
No question for me.
All right. Uh, Anyone else? Any questions? Okay. I'll assume that there are no questions. Let me. Okay. So, if I give you an example of that contains everything that we have been talking about before, let me give you an example of a pendulum. We have seen now that a pendulum is something that is like this and it's oscillating like this, right? So a mass attached to a string and it oscillates in these directions, right? So can you give me an example of how the law of conservation of energy apply in this case? This is the pendulum. What is happening? Anyone? How is the
There
conservation of it? Yeah,
there's some gravitational potential energy that is converted to kinetic energy, and there's some
right,
velocity.
right. Okay. Yes. So exactly. So when I raise this pendulum to some height, I'm giving it some gravitational potential energy as it's doing work against gravity. That gravitational potential energy is maximum at this point where I raise it, and then it starts. If as soon as I release it, it gains velocity. Now the velocity that it's gaining is the kinetic energy, which it's gaining by reducing potential energy but increasing the kinetic energy. So uh, in this case of a pendulum which is oscillating, we have a conversion from potential energy to kinetic energy, and then kinetic energy again gets converted back to potential energy, and this cycle continues until the bob comes to a rest at this mean position, right? Eventually it will come to this stop. Now do you understand why did I say that it would keep oscillating between these two energies, right? But so when you give it potential energy, it gets converted to kinetic energy, and it goes to this mean position. But now it has some kinetic energy, and it has maximum kinetic energy at this mean position. So it's going to get convert that into the potential energy by rising up some height, and then again that potential energy gets converted into kinetic energy, and the cycle continues forever. But practically, because there is some air resistance and so on, the thing it will stop due to friction, right? So that was just an example. Is that clear for everyone?
Yes, clear.
Okay, all right. So now let's talk about power. Okay, so what is power? Power is, so for example, suppose that you're doing work, right? When you're doing work, you're converting energies from one form to another. So work is basically uh, converting energies, right? You can say that work is converting energies from one form to another. You do some work, and now you want to check how fast can I do this work? How fast can energies be converted from one form to another? Now, this thing, you want to quantify it, and you do that with the notion of power. So power is then just the time rate, right, at which work is done, at which you can perform work, or you can convert energies, right? Because work is converting energies. So the rate at which you can do this thing is called power. And from this definition, you can write down the expression for power as the rate of work done, meaning work done per unit time. So W divided by T, which is what? Which is power, right? And work done is just converting energies. So you can write this as E over T as well. So this is work done, right? So I'll write WD. And so work or power is then measured in joules per second. So how much energy is used, converted, or how much work is done as every second passes. This thing is also called or redefined as watt, right? Watt. It's a unit for power. So is the idea of power clear?
Yes, clear.
Okay. So then uh, let's come to the reason why it's called power, right? Think of a machine. Now, if I have a machine and it converts more energy in a given time compared to some other machine. So, for example, here you have machine A, and here you have machine B. So, if the power for A is greater than power for B, meaning that if the machine A converts more energy in the same time and compared to machine B, then I'll say that machine A is more powerful compared to machine B, right? And that's why it's called power.
Yeah,
Now,
yes.
from this, right? So from this, we can talk about another concept, which is efficiency, right? Now, efficiency is related to energies, right? And of course, it is then related to power as well. Efficiency really tells you how much of the energy is useful. Now, all of the energy is not always useful, right? Some of the energy gets lost, or you can say converted into other forms of energies. Uh, and so let me give you an example. We know machines are used to do some work, right? So you can imagine some big machines in a workshop or anything, and they convert energy from one form to another. That's their job. Whenever machines are working, some of the work or energy gets lost into internal energies, sound energies, the sound that you're hearing of these machines operating. That's You don't need that. You don't need that really for the kind of work that you want that machine to do. But it doesn't matter, you still hear the sound, right? And that's the energy being converted into sound. So energy is being lost into something that you don't want it to
Also
be,
heat.
right? And also heat, exactly, right? So that's a very good example. uh, and so this will always happen no matter what kind of a machine that you can build. You can never build a machine that is always whose temperature never rises. You can never build a machine which is completely silent. So that means that energy will always be converted into a non-useful forms of energies, right? So that's where efficiency comes in. The only important variable is not how much output that I can get from a machine, but the efficiency, how much useful output I can gain from a machine. So then efficiency is just a ratio of, you can say, useful output to the total input, the total energy that I'm giving it, right? So you can write it as, or it's also written as useful work output divided by the total energy input. So you're giving it some all the energy, and how much useful work can be obtained from that energy. That's efficiency, right? So mathematically, sometimes efficiency is written with this symbol eta. It's called, let me write it. This symbol is called eta, right? And it is mathematically defined as the ratio of, how do I write it in short form? Let's write, or let me just write it, useful output divided by the total energy of the system, right? Total energy that you're supplying, total energy supplied, or total energy input, right? And then you just multiply this number with 100, and then you can get the efficiency. So you say my machine is 50% efficient. What does that mean? That means that if I'm giving
50% of the
100,
50% of
yeah,
50% of the energy are useful.
is useful, right? So exactly. So if I'm giving it, so suppose I'm giving it 100 joules of energy, then only 50 joules of that energy will be used to do something important, while the other 50 joules is completely wasted. That's how your cars also work. So when you use petrol, and not all, in fact, most of the petrol is wasted, and only some of the petrol is used to get the engine going, right? Most of the petrol is wasted, more than 50%, right? So no machine is 100% efficient, as always some of the energy will be lost into other forms of energy. Now that loss can be due to friction, or any other sort of thing, right? So due to friction, you can get losses like sound, you can get heat, and so on, right? So for example, if I were to compute the total energy supplied, or total input, the total energy that I'm giving to the system, then that total energy is just a sum of the useful energy that I got, or the useful output work that I obtained, plus all that wasted energy, right? So that's efficiency, right? And it is normally quoted as a percentage, right? So a system is 25% efficient, 50% efficient, 60% efficient. But what that percentage mean is that only if whatever the total energy is of that, only this percent of energy is going to be used to do something important. So that's efficiency. Is that clear for everyone? Any questions regarding the topic of
when you mean important, you mean like the machine was used to build, like for example, if I build it.
Exactly. So for example, you want to lift something using a machine, then important is for the machine is that it has to lift, right? So that's what I mean by important. So for example, a petrol, for example, I'll give you an example of petrol. By important, I mean a petrol is used for a car to get it going, get the engine running so the car can move. When I say important, I mean that if the petrol is doing its job, if it's getting the car going, then that's important. The other forms of energy are the wasted energy. We don't care. We don't want that. We don't care about that, but we cannot avoid it, right? So is that clear? So when you have
Yes.
have to design fuel tanks and all these things, how much fuel that a car should I put inside the car? You should always make sure that you uh, account for these factors, that only if I, for example, input 1 liter of petrol, only 0.2 or 0.5 or 0.4 liters will be used and get the car going. The other will be wasted. So you should always, whenever you're designing a tank for a car, a fuel tank, these factors should be considered. Right. So that's efficiency. Is that clear for everyone?
Yes, clear.
Okay. And so is the idea for power as well, I assume.
Yes, clear.
Okay. All right. Amazing. So let's do an example, right? And let's do a problem really, where we can understand the idea of power and this thing, efficiency, much more clear, right? So you have to remember that whenever we talk about energy, we're talking about conversion of energy from one form to another. Let's do an example where you have a, any stone, right? Suppose that you have a catapult and a stone is fired from that catapult, or any cannon, for example, right? So a stone is going to fly away, and suppose that the mass of this stone is 120 grams, and uh, suppose that the pebble accelerates from obviously rest. When it was sitting inside the cannon or in the catapult, its velocity was 0, but now that it's going to increase its velocity, and suppose it gains a velocity of 15 meters per second when the catapult fires it in 0.14 seconds. It gains this much velocity. I want you to tell me what would be the average gain in power of the pebble during the firing process. So what power did the pebble gain when the catapult fired it from itself to outside? So we want to compute the average power. Can you tell me how should I go about this thing? First thing, obviously, we'll convert these units, right? So only mass is the one that we need to convert. This would be 0.12 kilograms. Now, what would be the next step?
To convert this into
Yes.
kinetic energy, to convert it into kinetic
Right, to
energy.
write it as a gain in kinetic energy, right? Is that what
Yes.
you're saying? Right? Exactly. Right. So what do we see happening? We see that a pebble was at rest, it has nothing. A catapult fired it, so it gave it some, provided it with some force, and that now it has gained some kinetic energy as it has started moving, as it has gained some velocity, it has gained some energy. But what energy? Kinetic energy. Now the power that it has gained comes from this gain in kinetic energy, right? So if I compute the gain in kinetic energy and then divide it by in how much time did it gain this kinetic energy, I can get power. So it's very simple then, just to compute the gain in kinetic energy, half mv squared, right? Everyone remembers this expression for kinetic energy?
I remember.
Right. Okay. So everyone is following along?
I'm following
Hassan,
along.
Noor, Urva.
Yes, sir.
All right. Okay. Okay. So the gain in this kinetic energy is this thing, and now it's just a matter of doing some silly mathematics. You just put in the values, 0.12 kilograms multiplied by v. Velocity is 15 meters per second, so this 15 meters per second squared, and this will give you what would this give you? This would give you 13 point something, 13.5 joules, right? So that's the gain in kinetic energy. So I'll write it as Ke gain. This gain in kinetic energy provides the power, right? And so remember, power was energy per unit time. So the gain in power is gain in kinetic energy per unit time. So it is 13.5 joules divided by 0.14 seconds. And then you just have to do
Is it
mathematics, and this
is
gives
it
you
96.4
96.4 volts. Right?
volts?
Yes. Perfect. Good. Okay. So you can see the only thing that you have to understand when you read the question is what is it asking? What has the question provided you with? What is it asking? And then when you get to the mathematics, when you have figured that part out, then you get to the mathematics, and the mathematics is very simple because that you're also allowed to use the calculator. So the math part is always very easy. The what you have to understand is what's happening and what is the question asking, right? So in this part, you had to understand that what kind of energy would this pebble gain as it's fired from a catapult before it was sitting stationary at rest without any speed. So the energy that it can gain as soon as it starts moving would be kinetic energy. It gained kinetic energy. And if the question is asking you to calculate the gain in power from the of the pebble, excuse me. So that power gain in power comes from the gain in kinetic energy, right? Sorry. So that's this. Is that clear? Does everybody understand how did I compute the gain in power of the pebble?
Yes, I
During
understand.
this process? Right. Right. Is this clear for everyone? Okay, I assume that it's clear. I would really appreciate if you could let me know as well, just like Taha and Louise. Now let's okay, let's do another example. Let's try to involve efficiency as well. So let's see how can we do problems regarding efficiency. Okay, so I'm going to give you an example of a mortar that you supply petrol to give it some energy, and the job of the motor is to lift something up, right? So suppose that there is a motor. So I'm very terrible at drawing. Suppose this is the motor. I supply it some petrol. That means I'm giving it some energy, and then this motor powers this surface, and it's the motor's job is to lift it up, and so on. Now, suppose I put something on this surface. Suppose this surface is massless. Its mass is so small that it's considered massless. Then I put a bag on it, a heavy bag. The bag is so heavy. Say it's 2,700 kilograms, right? And I want to lift it about 12 meters high, right, from the ground. Now, I'm going to tell you this, that only 18% of the input energy is converted into this energy that I need to get it to some height of 12 meters. First of all, can you tell me what form of energy am I converting the petrol into?
Gravitational potential energy.
Exactly, right? Exactly. So the efficiency is what I'm telling you is 18%, meaning that only 18% of the total energy from the petrol is converted into the gravitational energy of the whatever this mass is. Suppose it's sand, right? Now, I want you to compute the input energy. So first of all, why not go ahead and compute the energy that I gave it, compute the input energy. The input energy is the energy from the petrol. So can you tell me how should I do this thing?
The 18% of the input energy is converted into gravitational potential energy. So you can add 82%.
Think about this. Okay, so 18% of the total energy, 80. So I'm giving it petrol, right? Now, only 18% of that petrol is going to be used to lift this mass to some height.
Yes.
So remember again, efficiency was the output that I'm getting divided by the input that I'm giving, right? And into 100, just so that we can cater for the percentage. This means, okay, so output is what? Output energy or output work that I'm getting is entirely the gravitational potential energy, or the work done from the gravitational potential energy. That is the amount of the output energy that I need, and that potential energy has a height of, or you can say includes the height of 12 meters, right? So the output that I'm looking for should be equivalent or equal to the gravitational potential energy, which is m times g times the height, where m is the mass of the this thing, 2700, then 9.81 is the acceleration due to gravity, and then the height is 12 meters. So the thing to understand over here is how much or what would the output be equivalent to? It would be equivalent to the gravitational potential energy gained by lifting it to that height.
Yes.
Right? So okay. So this is the useful work or the output work, or you give it any name for that matter, but it's the useful work done, which is exactly equal to the gravitational potential energy of the mass. And if you do the math,
It is 331,700, 7,520. 520
520. All right. Okay, great. So this is,
joules.
again, you have to remember in joules. Yeah, exactly. So this is the output that I was looking for. Now I can put this value in this expression. What is left? Input, but that we want to compute it. We are given the efficiency. So everything else is given, just one variable is missing, then you can rearrange the equation for that. So this becomes input energy, or the input energy from the petrol is output divided by the efficiency times 100, right? So this would be just then 317520 joules divided by 18% times 100%. So percent cancels, and you just have to do the math. Yes,
One
this would be
1764000. 17640 and another 0.
right. Okay, so this is again in joules. So this is the, so now let's look at the numbers and try to see what is happening. You gave you can write this as, if you remember your prefixes, you can write this as approximately equal to 1.8 megajoules, right? Mega was into 10 raised to power 6, right? This was a prefix. So look at this number, 1764000 joules of energy I gave to this motor by giving it some petrol, and only 317520 of that was useful in raising it to the height that I want it to. So you can, the motor is very inefficient in this case. So the 18% efficiency is very small. You should have used some other type of a motor. Maybe there is some problem in the motor that it's eating a lot of petrol. There could be any fault, right? Or just the motor is very inefficient to do this kind of work. Use some other motor, right? So that's what we can understand by the doing some of physics and then suggesting to the person, whoever is operating the motor, that you better start using a better motor. Anyway, so that's efficiency and power. With this, we can conclude the chapter of work, energy, and power. The next topic that we should be starting is pressure, where we'll talk about, pressure in different fluids like liquids. We'll talk about different instruments to measure pressure, discuss Pascal law and some of the applications of that Pascal's law, where we'll come across Boyle's law and so on. And so all of these things. How much time do we have left?
4 minutes.
Now 4 minutes. So I think we'll conclude this lecture with this, the meeting with this lecture of work, energy, and power. And we'll start the next topic of pressure and everything. And again, I'll try to increase the pace so that we can hopefully cover something. I was also going to do this thing. Do you have any problem if we have classes over the weekends? Maybe 1 or 2 classes over the weekends as well. Does anybody have a problem, or is it okay?
It's okay.
It's okay. All right. So then probably we'll be having 1 or 2 classes on Saturday, Sundays, right? I'll communicate the timings and everything to you in the group. Any other question regarding the things that we have covered so far? Anything that we have covered? Have you gone through the previous topics? Any question from any of those topics? Anything from this lecture?
No question
this
from
chapter?
the previous topics and this topic.
Right. Anyone else? Any question? Anything that you might be struggling with? Anything that you do not understand? Please do not hesitate. If you cannot unmute, and if you feel a bit of hesitation by unmuting and speaking, you can just type in the chat and let me know. Of course, you're registered for the course, and so you should be completely satisfied with the understanding So any queries, anything? Oh, by the way, Hassan, are you present in the meeting?
Yes, sir.
Right. So you have the problem with the timing as well, right?
Yeah.
You just come back from school at 3, I think. You
But
reach
like
home at 3.
5, I would say I'm free, and then I can take classes. But on Tuesday, it's especially difficult because my classes end on 2:30. Coming home takes like 30 minutes.
Right, right. So actually, the problem is that some students have other classes as well. Then we also have to manage AS and A2 classes as well. So I was looking into it. I thought that I figured the timing, but it turns out that there are some issues with that as well. So I'll look into that again, and for hopefully before Tuesday. Actually, tomorrow is Tuesday. Hopefully, before next Tuesday, I can sort this thing out. Until then, I'd really like to apologize for the issue of timing,
No
but
problem.
I'll get to that. Okay, so yeah, that's that. Any questions? Anyone? No questions? You should be asking questions. There should always be questions on your mind.
I have no questions on my mind. And less
No
than 1
questions.
minute.
All right. Okay. Yeah, you remembered that. Thank you. Okay. So, anyways, I think we'll end the lecture over here, and in the next one we'll start the topic of pressure, fluids, and something I like to call fluid dynamics as well. And so, yeah. Okay. So I'll end the class right now, and we can all.